Okay, so somebody asked a homework problem, so let's look at that and then start the next section. Make sure this thing is focused. Okay, so this is number 11 in 2-2. Remember, there's now two ways to do the determinant, by the definition, but now using the 7 properties in combination with theorem 1 and 2-1. Okay, so now we're doing it using the 7 properties of the determinant in combination with theorem 1 and 2-1. So here's the determinant. First thing we do is use Gauss-Jordan elimination to make it upper triangular. Every time we make a move, use the property to keep track of how this number, called the determinant, changes. Okay? So first thing, we need a 1 here. There already is a 1 there. So we're okay. If it wasn't, we know what to do. And we know how the determinant will change by property 2. But there is already a 1. Okay, so next we have to make these zeros. Yeah? So we do that elementary row operation. And remember, that doesn't change the determinant at all. That's property 7. And so we get this determinant. Okay, so do the row operation. You get that. Do the 3. It puts the 3 zeros here. Doesn't change the number, so it's still dead equal. Okay? Next, we need a 1 here. You see? We need to make that a 1. So we have to multiply it by 1 over 7. But that does change the determinant. Yeah, the determinant of that new matrix will be 1 over 7 times the determinant of the old one. But then the old one, which is right here, would be 1 over 1/7 times the new one. So we get 1 over 1 over 7 times the new one, doing this move. And that's by property 2. Didn't do the properties for nothing. Okay? Now that we've got a 1 here, we make these 2 zeros. Okay? You know what to do. We do these 2 elementary row operations. Okay? These 2 don't change the determinant by property 7. And so we'll be dead equal. Still have our 1 over 1 over 7. And you get this determinant. Next, we need to make this a 1. And zeros below it. Okay? So you got to multiply it by minus 7 over 2. But that does change this number by property 2. That new matrix would be minus 7 over 2 times the determinant of the old one. But then the old one, which is right here, would be 1 over minus 7 over 2 times the new one. So we get this. So we pick up another error term when we do this move by property 2. And we get this matrix, this determinant. Again, you got to multiply the whole row by minus 7 over 2. 0 times minus 7 over 2 is 0. 0 times minus 7 over 2 is 0. Minus 2 over 7 times minus 7 over 2 is 1. And minus 7 over 2 times 3 is minus 21 over 2. Okay? Just do the row. Now we have to make this a 0. You know what to do. Yeah? And that elementary row operation does not change the determinant by property 7. So we're dead equal again. And so we get this determinant. Of course, we still have our 1 over minus 7 over 2 and 1 over 1 over 7. Otherwise, dead equal by property 7. See, we didn't prove the properties for nothing. Kidding me? Okay, finally we are upper triangular. Take a look. Okay? We are an upper triangular matrix. Below the main diagonal, there's zeros. Okay? So now we can use theorem 1 in 2-1 that says the determinant of this matrix is the product of the diagonal entries. So you get this number, that times that product of the diagonal entries. Clean it up and then you're done. Here the 7's cancel, the 2 flips and hits this, but then it's in the top with the 14 makes a 7 along with a minus. So you end up with this. And then finally divide 7 into it and you end up with that. Capiche? Okay, so that's how all the 2-2 problems are done, using the properties, just like we did in the example we showed you. Didn't you watch that video? Come on, make sure you're watching these videos now. Okay, now let's go to the next section. Do the rest of them. Do all the assigned problems. Okay, so the next section is 2.3. And he entitles it Historical Proofs. Okay? Okay, so first we want to know what this number is that we're steadily computing, called the determinant. What does it have to do with invertibility? Okay? Otherwise, it's just a number to ask you to compute over and over again. What good is that? Okay? And in this section, we're going to see it has everything to do with invertibility. It totally determines it. Okay. So I'm gonna make up some notation here. I'm gonna let ES, S standing for switch, be the n by n elementary matrix. Some people forgot what an elementary matrix is. Back in 110, elementary matrix that is obtained by switching 2 rows of IN. Okay? So you got to remember, from now on, I'm going to call it ES for E-switch. Okay? So it's the elementary matrix obtained by switching some 2 rows in IN. Okay? I'm going to let EM, standing for multiply, be the elementary matrix that's obtained by multiplying a row of IN by some non-zero number. I'll call it C. Okay? Be the n by n elementary matrix obtained by multiplying. That's why we're using an M. Multiplying. Multiplying starts with an M. IN by C, I'll say. Some non-zero number. Okay? So we're going to call that elementary matrix EM because it's obtained by multiplying a row of IN by something. And E-switch, ES, it's obtained by switching two rows of IN. There's finally only one other elementary matrix to give a name to, and that's the one that's obtained by multiplying a row of IN by something and adding it to another row and using it for that row. So you're multiplying and adding, I'll use MA, multiply, add. So I'm going to let EMA be the n by n elementary matrix obtained by multiplying a row of IN by some non-zero number, I'll say C, comma, adding it to another row, comma, and using it for that row. You know, it's our third elementary row operation. And using it for that row. So I'm going to call it EMA. Okay? So you got E-switch, E-multiply, and add. Capiche, capash, capoche? Let's prove the theorem. So this is lemma 1 and 2, 3. And this is lemma 1 and 2, 3, and it goes like this. One, the determinant of E switch is -1. 2, the determinant of E multiply is C. And 3, the determinant of E multiply and add is 1. Okay, so let's prove it. Let's start off with 1. For 1. Well, let's look at the determinant of E-switch. Remember what E-switch is? It switched two rows of IN. But by property 4, its matrix, its determinant will be negative the determinant of IN. So it would be -1 times the determinant of IN. Why? By property 4 that we prove, baby. Should always be able to prove all 7. Okay, now I'm going to work on this number. Do you know the determinant of IN? It's upper triangular with 1s down the main diagonal. So it's determinant by theorem 1 and 2, 1. It's a product of those diagonal entries. When you multiply n 1s together, you get 1. So that's equal to -1 times 1. And that, of course, is 1. And congratulations, You prove the first one. Okay? Or sorry, that's minus 1. Sorry, minus 1 times 1 is minus 1. Yeah? So you get minus 1. And you've proven this first one here. Okay? So the determinant of in is 1. You have a minus 1 here. Multiply them, you get that. Okay, let's do 2. For 2. Let's prove 2. Let's look at the determinant of EM, E multiply. Remember how it's formed. It's formed by multiplying a row of IN by a non-zero number C. By property 2, its determinant would be C times the determinant of IN. Why is this true? By property 2, that you all know how to prove. Okay? Now I'm going to work on this number. The determinant of IN is 1 because it's upper triangular, and so its determinant is the product of the diagonal entries by theorem 1 into 1. And all the diagonal entries are 1. And when you multiply all those 1s together, you get 1. So its determinant is 1, so it's C times 1, and that's C. And congratulations, you've proven the second one. Okay? And that's thing 2. Okay, the last one, thing 3. For 3. Some people are still trying to do number 11 and 2 too. Shame on you. Okay, let's look. Look at the determinant of E, multiply and add. What can we say that's equal to and why? Okay, if you remember multiply and add on the previous page we just talked about, it's obtained by multiplying a row of IN by a number, adding it to another row, and using it for that row. By property 7, its determinant is the same as the determinant of the matrix you made it from, IN. So that's equal to the determinant of IN. Why? By property 7. And the determinant of IN is 1. So you have just shown the third one. Okay? So there you have it. You can put your little box there, baby. Baby, baby. Let's prove another lemma. This is lemma 2 and 2, 3. This is lemma 2 and 2, 3. It goes like this. Let A be a n by n matrix and E be a n by n elementary matrix. Okay? So you got a matrix and an elementary matrix. Then we claim, then, if I multiply them, then take the determinant, it's the product of the determinants. In other words, the determinant of EA with the E on the left is equal to the product of the determinants. Never knew all this stuff about the determinant from Calc 3, did you? Shame on you. Okay, let's prove them, baby. Now, since E is elementary, there's only 3 types. Yeah? There's ES, EM, and EMA. So I'm going to check this on all three. And if it checks out, then we've proven it. Because there's only three types of elementary matrix. Because there's only three elementary row operations to do on IN. Capiche, capash, capoche? Prove it. Prove. Okay, let's check ES. See if it does it for ES, E-switch. Okay? If I look at the determinant of E-switch times A, remember by Theorem 1 in 110, when we multiply on the left a matrix, which we're doing here, by an elementary matrix, it does that row operation on the matrix for you. So this is the matrix that has two of A's rows switched. But by property 4 in 2, 2, that's equal to minus the determinant of the old matrix A. So I'll say it like this. This is minus 1 times the determinant of A, Y, by property 4 in Theorem 1 in 110. Some people forgot what 110 was. Okay. Yeah? Now I'm going to start to do stuff with this number minus 1. From the last lemma, we remember that we just proved lemma 1 in 2, 3, we just proved it just a minute ago, is that negative 1 is the determinant of E-switch. So I can replace this minus 1 with the determinant of E-switch. So that's equal to the determinant of E-switch, and then bring your determinant of A down. And the theorem's proved. When E is E-switch. Yeah? Okay? What if you're E multiply? Let's check that. Let's check E multiply. Well, let's look. Let's look at the determinant of E multiply by A and try to compute it legally, of course. And let's give a reason to this last step, okay? Remember, this one's by lemma 1. In 2, 3, the section we're in now. The reason why minus 1 is that number. Woo! Okay? So give a reason there. Okay, so let's go down here and check E multiply. Okay? So by Theorem 1 in 110, when we multiply on the left by an elementary matrix, it does the elementary row operation on the matrix for you. So this is the matrix that has a row of A multiplied by the number C. By property 2 in 2, 2, its determinant is C times the old matrix, the determinant of A. So I'll say it like this. This is C times the determinant of A. Why? By two things. By property 2 this time, in Theorem 1 and 1.9. In 110, rather. In Theorem 1. In 110. Okay, now I'm going to play around with this number right here. Yeah, right here. We just found out in lemma 1 in 2, 3 that we just proved a minute ago is that this number is the determinant of E multiply. So I can replace it by the determinant of E multiply. So that's equal to the determinant of E multiply, and then bring your determinant of A down. And congratulations, you have just now showed these are equal. And remember, the reason why C is this determinant was that lemma we proved a minute ago. It's by lemma 1 in 2, 3. Okay? Check the final possible type of elementary matrix, E, multiply and add, and the theorem will be done. Okay, so let's check E, which we agreed to call this a minute ago, MA. Okay? Well, if we look at the determinant of E, multiply and add times A, by theorem 1 and 110, this is the matrix who has a row of A multiplied by a number C, added to another row and used for that row. Yeah? So by property 7 in 2, 2, that doesn't change the determinant at all. So that's equal to the determinant of A. Why? I'll tell you why. By property 7 this time, which you all can prove, and theorem 1 and 110. Okay? Now I'm going to play around with this number. Some people think that's a matrix. That's a number. It's like 17 or something. So a number is equal to 1 times itself. So I can multiply that by 1 if I want to and not change it. Okay, so that's equal to that. And now I'm going to play around with this number 1. We found out in lemma 1 in 2, 3 that we just proved a minute ago is that 1 is the determinant of E multiply and add. So I can replace the determinant of E multiply and add by the 1 if I want to. And guess what? I want to. So I can replace that by the determinant of E multiply and add and bring your determinant of A down. And congratulations, you proved it happens in the third case as well. And so since these are the only 3 types of elementary matrices, it always happens for every elementary matrix. And the theorem's proven. Okay? With that being said, finish your homework problems and we'll probably deliver your last lecture probably tomorrow night sometime, just to finish up this 2, 3. There's only like 2 more theorems to prove. Stay safe and make sure you do all your problems and keep loving that linear algebra.